I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss some numericals based on the concepts in optical fibers. So before we do the numericals, let us have a quick recap of the formulae that we are going to use. So the first one is to calculate the critical angle. Theta c is equal to sine inverse n2 by n1. So here, what is critical angle? So critical angle is the angle at which the light has to be incident for total internal reflection to occur. So whenever we are talking about communication in optical fiber, the communication is occurring due to total internal reflection. The signal is propagating through the fiber due to total internal reflection. So we need to know the angle, the critical angle based upon the materials that are used. So theta c is equal to sine inverse of n2 by n1. So theta c here represents the critical angle. It is the angle at which the angle of refraction is equal to 90 degree. And n1 represents the refractive index of core. The first medium, here we call it as core because the signal comes from the core to the cladding. So n1 is the refractive index of the core and n2 is the refractive index. I'll write it as Ri, refractive index of cladding. Next comes the numerical aperture. Numerical aperture gives us the light gathering capacity of the optical fiber. So numerical aperture is given by under root n1 square minus n2 square. So n1 is again the refractive index of the core, n2 is the refractive index of the cladding, and it also depends upon the medium from which it is incident. So whenever we are talking about an optical fiber, this is the core, this is the cladding, now when the signal is being launched into the optical fiber, so we have something called acceptance angle. So the light is coming from air here. It is going into the core and this is the interface of the core and the cladding. So there will be total internal reflection here. So the medium from which it is launched also matters and the refractive index of this is denoted by N0. So N1 for core, N2 for cladding and N0 for the medium through which it is launched. We also have another formula if you know the acceptance angle. So numerical aperture is equal to sine theta A. Theta A here, NA represents the numerical aperture. And theta A represents the acceptance angle. So what is the significance of this acceptance angle? Why do we have to know about this acceptance angle? Means the angle at which it has to be launched for light to propagate through the optical fiber. It all depends upon how it is launched. So theta A is very important. That is the angle, the acceptance angle. We have an acceptance cone and all the signals that are launched through the acceptance cone will propagate very easily through the optical fiber. So NA is equal to sine theta A. And if we want to calculate theta A, So theta A will be nothing but sine inverse of NA. So once you get the acceptance angle, you can calculate the numerical aperture, or knowing the numerical aperture, you can calculate the acceptance angle. Also, we have one more formula for the refractive index, change in refractive index delta. Delta is given by N1 minus N2 upon N1. N1 is the refractive index of the first medium, that is core. N2 refractive index of the second medium upon N1 again the refractive index of the medium. This gives the fractional change in refractive index. This is what we call it as fractional change in refractive index. We also have another formula to calculate the numerical aperture in terms of delta. If the fractional change is given, how do we calculate the numerical aperture? That is N1 under root 2 delta. Or this can also be written as N1 into 2 delta power half. So these are the formulae we are going to use to solve the numericals now. So coming to the first numerical, calculate the numerical aperture and acceptance angle of a given optical fiber if the refractive indices of the core and the cladding are 1.563 and 1.498 respectively. Means this will be the refractive index of the core and this will be the refractive index of the cladding. So we have discussed different steps when we are doing the numericals. Though the first thing is to identify the given data. In identifying the data, what is given and what we have to find out. So what is given here is the refractive index of the core. So I will denote the refractive index of core by N1. So N1 is equal to 1.563. This is for the core. N1 is representing the core refractive index. Then N2 is equal to 1.498. This is for cladding. We are given N1 and N2, and what we have to find is the numerical aperture, and we also have to find the acceptance angle theta A, NA and theta A. So what is the formula we have for numerical aperture? We have seen numerical aperture is given by under root N1 square minus N2 square. Under root N1 square minus N2 square. So let us substitute the values of N1 and N2 here. Under root 1.563 square minus 1.498 square. So you can do this calculation using your calculator. It's a very simple calculation. 1.563 square minus 1.498 square, and then take the square root. So we get the numerical aperture as 0.45. And now the next thing is to find the acceptance angle. So theta A will be equal to sine inverse of numerical aperture. So since we have got the numerical aperture, we can easily calculate the acceptance angle. So sine inverse of 0.45. Sine inverse of 0.45 will be equal to 27 degree. So this is the acceptance angle. So acceptance angle means the angle at which it has to be launched inside the fiber for it to propagate very easily through the optical fiber. And the numerical aperture tells us about the light gathering capacity of the optical fiber. Now the second one. In an optical fiber, the refractive index of the core is 1.52. So RI, refractive index of the core, is 1.52. And the refractive index of the cladding is 1.48. We need to calculate the critical angle. So let us write the data. Data given. Refractive index of the core always denoted by N1. So N1 is equal to 1.52. And the refractive index of the cladding is denoted by N2, 1.48. So this is always representing core and this is representing the cladding. So the refractive index of the core and the cladding are given. We have to find the critical angle. Here C represents the critical angle. For acceptance angle, we have taken theta suffix A, and for critical angle, we are taking theta suffix C. So theta C is equal to how much? Critical angle. So let us write the formula. Very simple formula we have. Theta C is equal to sine inverse N2 by N1. Refractive index of the cladding upon the refractive index of the core. Sine inverse of N2 by N1. So let us write sine inverse N2 by N1. N2 is 1.48 and N1 is 1.52. So 1.48 upon 1.52 will give us 0.97. Now you can use the calci and find sine inverse of 0.97 is equal to 76 degrees. So the critical angle for this pair of core cladding having refractive indices 1.52 and 1.48 is 76 degrees. Now the third one. The core of an optical fiber is made of glass of refractive index 1.55 and it is clad with another glass of refractive index 1.48. So this is the refractive index of the core and this is the refractive index of the cladding. Determine the numerical aperture, the acceptance angle and the critical angle. Here we are going to find all the three. So we'll write the data. N1, 1.55. This is for the core refractive index. N2, 1.48. This is for the cladding. We have to find the numerical aperture first. Then we will find the acceptance angle, theta A, and then we will find the critical angle, theta C. So let us write the formula and find one by one. So first formula for numerical aperture. Numerical aperture is given by under root n1 square minus n2 square. N1 square minus N2 square. So this is equal to under root 1.55 square minus 1.48 square. So that gives us 0.46. So the numerical aperture is 0.46. And then comes the acceptance angle. Theta A is sine inverse of NA. So it is sine inverse of 0.46. So that will be 27 degree. The acceptance angle is 27 degree. Then the last one is the critical angle. Critical angle is given by sine inverse N2 by N1. Sine inverse of N2 by N1. So we can substitute the values of N2 and N1 1.48 upon 1.55. So this is sine inverse of 0.95, which will be equal to 72 degrees. So the critical angle for a core of refractive index 1.55 and the cladding of refractive index 1.48, it is 72 degree. Next one, calculate the fractional index change for a given optical fiber if the refractive indices of the core and the cladding are 1.563 and 1.498. So let us write the data. What is the fractional change in refractive index we are going to find? So for the core, it is 1.563. So let us represent it by N1. N1 is equal to 1.563. And for the cladding, 1.498. So N2 is equal to 1.498. What we have to find is the fractional index change. Delta we have to find. So what is the formula for delta we have for the fractional change in refractive index? Delta is equal to N1 minus N2 upon N1. N1 minus N2 upon N1. So what is the value of N1 here? 1.563 minus 1.498 upon 1.563. So we get 0.042. So for all calculations and simplifications, you can use your calci. So once you start using it while practicing, it becomes very easy. So the refractive index for a given core cladding combination is 0.042. And because it is a ratio of two numbers or the refractive indices of same quantities, so there is no unit, it is simply a number. The fifth one, a step index fiber has a numerical aperture of 0.16 and core refractive index of 1.45. Calculate the acceptance angle and also the refractive index of the cladding. So what we have to find, we are given the numerical aperture, we are given the refractive index of the core, we have to find the acceptance angle and then the refractive index of the cladding. So let us write the data. Numerical aperture 0.16. Refractive index of the core 1.45. So this is for core. We have to calculate theta A and also we have to find N2, that is the refractive index of the cladding. So two quantities are given and we have to find two quantities, theta A acceptance angle and N2 the refractive index of the cladding. So let us write the formula. First we'll find acceptance angle. Theta A is equal to sine inverse of NA, numerical aperture. Since the numerical aperture is given, we can easily find the acceptance angle, sine inverse of NA. So this is sine inverse 0.16. That is 9.2 degree. So the acceptance angle is 9.2 degree. And then the next one is we have to calculate the refractive index of the cladding. We know the numerical aperture and we also know the refractive index of the core. So we will use the formula NA is equal to under root N1 square minus N2 square. This is a known formula. Now NA is given, N1 is given, we have to find N2. It is better to write the formula for N2 and then substitute, it becomes easy. So for this, I do squaring on both the sides. So we have numerical aperture square is equal to N1 square minus N2 square. Okay, we are squaring on both the sides, so the square root goes off. We have n1 square minus n2 square. Because we want to find n2, I will take this n2 the other side and bring na onto the right hand side. So this minus n2 square, if it comes onto the left hand side, it becomes plus n2 square is equal to n1 square. This plus na square will become minus na square. n2 square is equal to n1 square minus na square. We want to find only n2, so we will take the square root. What we are trying to do is, whatever we have to find, we are writing it in terms of known quantities because we know n1, we know na. So we have written it in terms of known quantities. So n2 is equal to under root n1 square, that is 1.45 square minus na, that is 0.16 square. So this gives us 1.4. So the refractive index of the cladding is 1.4. The sixth one, calculate the refractive indices of the core and cladding of a numerical aperture with a numerical aperture of 0.33 and the fractional difference of refractive index being 0.02. So we are not given the refractive index of the core and cladding, both we have to find. We are given only the numerical aperture and the refractive index change. So first write the data. NA is equal to 0.33 and delta is equal to 0.02. What we have to find is the refractive index of the core, and we also have to find the refractive index of the cladding. Na for core, N1 for core, N2 for clad. So here we'll use the formula of Na in terms of the fractional change in refractive index. While discussing the formula, we have seen that the numerical aperture can be written as N1 under root 2 delta. We have to find N1. So we will find first N1 and then N2. So N1 can be written as Na upon root 2 delta. Why I am using this formula? Again, I am writing it in terms of known quantities. We know the numerical aperture and we also know the fractional change in refractive index. So we are writing it in terms of known quantities. So N1 is equal to Na is 0.33 upon root 2 into delta is 0.02. So what we have here is 0.33 upon under root 0.04. So N1 we get as 1.65. So once we get N1, we can find N2. So what is the formula we have derived just now for N2? N2 is equal to under root N1 square minus Na square. We have derived it from the formula of Na. So N2 is equal to under root N1 square minus Na square. So what is the value of N1 we got? 1.65 square and Na is given as 0.33 under root. So this gives us 1.5. So N2 is equal to 1.5. N1 is equal to 1.65. So this is N1, the refractive index of the core, and this is N2, the refractive index of the clad. Now the seventh one. The numerical aperture of an optical fiber is 0.39. Numerical aperture is given. If the difference in the refractive indices of the material of the core and cladding is 0.05, calculate the refractive index of the material of the core. So let us first understand and write the data. The numerical aperture is given NA is equal to 0.39, and here the difference in the refractive indices of the material of the core and cladding means N1 minus N2 is given 0.05. The fractional change is not given here. They have just given us the difference in the refractive indices of the core and cladding, that is N1 minus N2 is 0.05 given. We have to calculate the refractive index of the material of the core. We have to find N1. Okay, so it is understood. NA is given and the difference in the refractive indices are given. We have to find N1. So which formula we will use? We will definitely use the formula of numerical aperture involving the change in refractive index. So NA is equal to N1 under root 2 delta. NA is equal to N1 under root 2 delta. I'm going to take the square on both the sides. So NA square is equal to N1 square into 2 delta. Square and the square root goes off. We have NA square is equal to N1 square into 2 delta. And now we know the formula for delta. What is delta equal to? N1 minus N2 upon N1 is the formula for delta. We are substituting the formula for delta. I'll write here, since delta is equal to N1 minus N2 upon N1. So this N1 and N1 gets cancelled. So what we have here is 2N1 into N1 minus N2. What we have to find here, N1? So I'll write the formula for N1 from here. So N1 is equal to, NA square. NA square upon 2 into N1 minus N2. So is it clear why we are writing the formula in terms of NA and N1 minus N2? Because we know NA and we know the change in refractive. We don't know N1 and N2, but we know the change in refractive index, that is N1 and minus N2. So we have written it in terms of known values again. So N1 will be now equal to 0.39 whole square upon 2 into 0.05. So I can simply write it as 0.39 whole square by 2 into 0.05 will give us 1.521. So the refractive index of the core is 1.521. So even if you have to calculate the refractive index of the cladding, you can use the formula N2 is equal to under root N1 square minus NA square. Because we are given NA, we have found N1. So substituting in this equation, we can also get the value of N2. Here in this problem, it is not asked. We are asked to find only the refractive index of the core. Even if we have to calculate N2, the refractive index of the cladding, we can use this formula and find N2. Next, an optical fiber has a refractive index of core and cladding 1.48 and 1.45. Find the acceptance angle in water which has refractive index 1.33. So let us write the data. Refractive index of the core. So N1 is equal to 1.48. This is for the core. N2 is equal to 1.45. This is for cladding. Now, in all the other problems, we have considered the numerical aperture to be equal to under root n1 square minus n2 square only, because the refractive index is not given. So we have assumed that it is launched through air, and n naught is equal to 1 for air. So whenever we are given that the signal is launched through air, we take n naught is equal to 1. So therefore, there is no denominator, something upon 1. We have only under root n1 square minus n2 square. Or if it is not mentioned also, we consider that it is through air. But here it is specifically mentioned that it is launched through water of refractive index 1.33. So we consider n naught as 1.33. This is for the refractive index of water. And we have to calculate the numerical aperture and also the acceptance angle in water. So first we'll find the numerical aperture. Numerical aperture is equal to under root 1.48 whole square minus 1.45 square upon 1.33. n1 square minus n2 square upon n naught. So we get the value as 0.2229, or we can approximate it and write it as 0.223. So we have got the numerical aperture. So once we get the numerical aperture, we can calculate the acceptance angle. Theta A is equal to sine inverse of NA. So this is sine inverse of 0.2229. So that is 12.879 degree. So the acceptance angle when the fiber is immersed in water is 12.879 degree. The next one, an optical fiber has a numerical aperture of 0.02 and a cladding of refractive index 1.59. Find the acceptance angle for the fiber in water which has a refractive index of 1.33. So here the numerical aperture is given. We are not given the values of n1 and n2. We are only given the refractive index of the cladding. So if you know the numerical aperture, we can easily calculate the acceptance angle, and that too we have to find the acceptance angle in water whose refractive index is 1.33. So let us write the data. NA, the numerical aperture is 0.02 and the refractive index of the cladding is 1.59. This is for clad. We have to find the acceptance angle in water. So when we have to calculate the acceptance angle in water, we will first calculate the numerical aperture in water and then we can simply find theta A. So we know the formula. Numerical aperture is equal to under root n1 square minus n2 square upon n naught. Because it is in water, it is not through air. Only for air, n naught becomes 1 and we write Na is equal to under root n1 square minus n2 square. So here we are given the numerical aperture, that is in air. So under root n1 square minus n2 square is given as 0.02 divided by the refractive index of water, that is 1.33. So what we get here is 0.15. So the numerical aperture is 0.15. So you need to understand here, when we are writing under root n1 square minus n2 square alone, means it is launched through air and the numerical aperture is 0.02 in air. Now when it is immersed in water, what is happening? We are dividing it with the refractive index of water and we get the numerical aperture. So calculate the acceptance angle in water. So theta A is equal to sine inverse of numerical aperture. So sine inverse of 0.15, that is 8.6. So the acceptance angle is 8.65 and the numerical aperture is 0.15. Now the 10th one. When the mean optical power launched into an 8 kilometer length of the fiber is 120 microwatts and the mean optical power at the fiber output is 3 microwatts. Find the overall signal attenuation and the signal attenuation per kilometer. So we'll have to find the attenuation coefficient per kilometer. So write the data first. What is the length of the optical fiber? Given as L is equal to 8 kilometer. The mean optical power launched means the power input is 120 microwatts. And the mean optical power at the output. So the output power P0 is 3 microwatts. What we have to find is alpha. That is the attenuation coefficient alpha we have to find. So what is the formula we are going to use here? For alpha, alpha is equal to 10 by L. Per kilometer we have to find log to the base 10 pi upon p0. So this is the formula for finding the attenuation coefficient. So here we are having this power input in microwatts. So we will convert it into watts. Here both are given in microwatts, so there is no problem. But still we need to convert everything into the same system. So we'll write this also in watts. So 1 micro is 10 power minus 6 watts. And 3 microwatts is 3 into 10 power minus 6 watts. So let us substitute these values here. We get 10 by L log to the base 10 pi. Pi is 120 into 10 power minus 6 upon P0 is 3 into 10 power minus 6. We are just substituting the values of Pi and P0. So 120 by 3 into 10 power minus 6 by minus 6. So these two will get cancelled. So we have 10 by L log to the base 10. 120 by 3 will give us 40. Log 40 to the base 10. And we know from the logarithm books or using your calci, you can find the value of log 40 to the base 10. That will be 1.6. Now 1.6 into 10 is 16 and the value of L is 8. So 16 upon 8 will give us 2 dB per kilometer. So we are dividing with the length that is given. The length of the optical fiber is 8 kilometer. So it is 16 upon 8, that is 2 dB per kilometer. So the overall signal attenuation we are writing in terms of the attenuation coefficient. Alpha is equal to 2 dB per kilometer. So thank you and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.